Hello. So we have solved an ideal Brayton cycle problem in example 1. Then we have solved example 2, which was an actual cycle in which isentropic efficiencies of the turbine and compressors were introduced. And now it's time that we go make the problem even more complicated. So in this example, we want to introduce a reheat to this problem. Again, in chapter 8 of your textbook, in the textbook, these are discussed in details. I'm assuming you understand, you know what reheating is all about. So let's go and understand the TS diagram for a reheat cycle. Again, the original problem that we have already solved, that looks something like this. We had this actual cycle where we had 1, 3, 4, 6 was our actual cycle, and to that cycle we are introducing the reheat. So as you can see, the state 5 and 6 will move up to an intermediate pressure because the turbine is split into two different turbines, high pressure and low pressure turbines, and there'll be 7, 8, 9. There'll be three new states where 7 is our reheat state after raising the temperature by reheat. So the reheat temperature is given in this problem, if you notice, 1400 Kelvin, and that will become crucial in finding this state. Also, we need a pressure ratio. Even though we know the overall pressure ratio to be 10, we need a pressure ratio for the high pressure and low pressure turbine. Only one of them needs to be given, and in this case, for the high pressure turbine, is given a pressure ratio of 3. So in other words, there will be a pressure ratio of 3 here and 4 there. That said, let's go and reproduce the previous problem we solved, this one, and then our strategy would be to modify state 5 and 6 and introduce state 7, 8, 9, and then recalculate the devices. Obviously, high pressure turbine, low pressure turbine, and the reheat, these all three have to be recalculated. Okay, so now that we know the strategy, let's go and first reproduce our old solution. Go back to the power cycle PG model. Here are all our examples, and this is example 2 is where we are starting from. Let's copy the test code, launch the app, paste it on the I/O panel, load, and voila. We have our solution now. You can see that it matches the answer of the previous question. So let's isolate all the variables we define. Let's introduce new variables like P ratio of the high pressure turbine, HP turbine 1 equal 3. Notice we don't need the high pressure, low pressure turbine ratio. This can be automatically obtained. We have a new variable, temperature of the reheat, 1400 Kelvin. And notice we have two turbines, and let's define turbine 1 has a efficiency of 0.9, 90%, and the second turbine has the same value, but it's wise to put a new variable to it so that we can change it later. So these are our overall parameters of the problem. If I do a calculate, they're all registered. We be careful with the naming. Okay, so now we go back to the state panel, and we know that state 1, 2, 3, 4 do not change. You can go back to the TS diagram to verify that. State 5, on the other hand, will be different because pressure at 5 is no longer P5, it is P2 divided by P ratio, P ratio, DIO, of the high pressure turbine HPT1. If I've done that right, yes, we found state 5. You can go to the graphic panel to make sure state 5 should be a little bit higher than 6 right now. Yes, so let's go and correct state 6. State 6 should have the same pressure as state 5, but enthalpy is going to be different. The enthalpy is going to be eta of turbine 1. So notice my enthalpy formula is H4 minus H5. Again, I have already, just to show you my cheat sheet, has developed the enthalpy relations for H6 and H9 using the turbine efficiencies. So I'm basically cutting and pasting these formulas in this space. So H6 is now known, therefore state 6 is calculated. State 7 would be a completely new state because I don't think I have one. If I go to state 7, there is nothing. So instead of starting a brand new one, I'm cloning this, but I know it will be P7 will be same as P6. Yes, that's correct. And instead of H7, we know the reheat temperature. This would be equals T reheat. So therefore, state 7 is now calculated. To get state 8, we know pressure will be equals P1 and entropy will be equals S7. So therefore, the isentropic exit state, we should have cloned the state, would have been a little bit easier, m dot 1. So state 8 is now calculated. For state 9, I have already entered P9, m dot 9, and now H9, according to my isentropic formula, is H7 minus H8 times efficiency of the second turbine, T2. So if this is correct, I should get state 9 correctly. And if you go to the graphics panel, they should now make sense. 4, 5, 6, 7, 8, 9, exactly as we expected. Now that we are done with all the states, time to go and visit the devices back. Again, device 1, nothing changed. Device 2, nothing changed. Device 3 actually goes from 4 to 6. That's the first turbine. So again, the numbers will change. We should calculate everywhere if any number changes anyways. And then, so we're done with device 3. Let's go to device 4, which is a reheater now. So device 4 is going to work between 6 to 7, and no work transfer. So this is our reheater. And device 5 is our second turbine going from state 7 to state 9. 7 to 9 is the turbine and the heat transfer is 0, so output is found. And finally, 9 to 1 is the heat exchanger that brings us back to the inlet condition of the compressor. And of course, there is no heat transfer, so there is no work transfer, there is heat transfer only. So looks like we finished all the processes or all the devices. So therefore, as you can see, the cycle is complete now, and we have found w.net 5028 q.net, they're equal. And here is my thermal efficiency, the new thermal efficiency after we added the reheat. It seems like it went down slightly. We had 39 point something before anyways. And just to make sure we get back the old results, just suppose you want to go back and want to get the previous result. How can we simplify it? Well, if we make the first turbine disappear, how can you do that? If we call the first turbine as a pressure ratio of 1, and then the reheat temperature, basically it stays the same state, 1500. So if you now look at that, if you calculate now, everything else should go back to the previous problem's situation if you do a super calculate. So if you come back to the graphics panel, if you notice, the plot becomes, the TS diagram resembles the old one, except the state numbers have moved slightly, and you can see that we get back the previous thermal efficiency of the cycle. So in other words, now we have a more general solution, and we can change these numbers to go back to any problem we have solved so far. Also, think of the wide variety of parametric studies you can do with these numbers. Again, we are going to build further on this and add a regenerator in the next example.